I welcome all the students. We have started learning the unit number 4, okay, and we have already covered the point, okay, viewing transformation, okay. So today we are going to learn the point windowing transformation. So our point of discussion for today's session is windowing transformation, okay. So once we cover the windowing transformation, we may have the next point in our syllabus, okay, clipping operation, point and line clipping, polygon clipping, and so on, okay. So but today we are going to focus on the point windowing transformation, okay. So let us start understanding the concept of windowing transformation. Okay, you can find the heading as windowing transformation here. And now we just consider the point window to viewport coordinate transformation. That is nothing but we are considering it as under the windowing transformation. We are going to transform the coordinate from window to viewport. Okay, so what we have already learned the point viewing transformation. Okay, so generally what we are going to do is once the object description have been transferred to the viewing reference frame, we choose the window, extend in viewing coordinates, and select the viewport limit in the normalized coordinates. Okay, so we have seen this in the viewing transformation, and after this we generally call it as the final step is object description are then transferred to normalized device coordinates or screen coordinates. Okay, so whatever the object we have captured in the windowing or window, or we can say it as we have captured in board coordinate system. Okay, whatever the object we have or object description we have captured in the board coordinate system with the help of window are then transferred to the normalized device coordinate system, and in normalized device coordinate system we are going to use the viewport. Okay, so viewports are used in the device coordinate or screen coordinate system. Okay, now how this is done? This is done by using a transformation, or to achieve this we are using a transformation that maintains the same relative placement of objects in normalized space as they had in the viewing coordinates. Okay, so this is done again with the help of the transformation that maintains the same relative placement. Okay, relative placement relative to the window. Okay, and I'm displaying it into the viewport. Okay, I'm converting it into the viewport. The object is normalized space. Okay, displaying the object in normalized space as they had in the viewing coordinate. Okay, now if a coordinate position, for example, we are considering the coordinate position is at the center of the viewing window. Okay, so in the viewing window, I'm having the coordinate position at the center. Suppose the object is displayed at the center of the window or in the word coordinate system. What we have to do is it will be displayed at the center of the viewport. Means in the viewport also it should be displayed at the center if the object was captured in a window and at the center of the window. Okay, so this is what we have to maintain. Okay, now this is the something which we call it as the window to viewport mapping. This process we are calling it as window to viewport mapping, or we are calling it as window to viewport coordinate transformation. We have mentioned this point as a heading, window to viewport coordinate transformation. Okay, so let us understand this in detail with the help of the formula, diagram, whatever the additional detailing we required. Okay, so that we want to understand or we want to learn window to viewport mapping. Okay, so I'm just moving to the next slide to continue with the discussion. Now this diagram is very important for us to understand the windowing transformation. Okay, now just look at the understand. I first read the description of the diagram. A point at the position x, w, y, w. Okay, x and y values. This w indicate it is defined the point in the window. Where the window exists in the world coordinate system. Okay, in a designated window is mapped to the viewport coordinate xv comma yv. Okay, so here xv indicate the x and yv indicate x and y coordinate of a viewport v. Okay, so this v indicate viewport, and viewport means definitely it is the area which is there on my display screen or device coordinate system, so that relative position in the two areas are the same. Okay, so I want everyone to look at this particular diagram in detail. So this is, suppose I considered this is my diagram number A. Getting me? Now this diagram number A is represent it in the world coordinate system. Okay, whereas this diagram number B I consider it is represented into the screen coordinate system or device coordinate system. Okay, this is represented in device coordinate system. A is represented in the world coordinate system. Okay, now if you can find this rectangle in the diagram number A, whatever this rectangle is there, this is nothing but, I just mention it as, right, W indicate it is my window. Okay, so this is my window in the world coordinate system, and in the diagram number B, whatever the rectangle I am finding over here, this rectangle is represent the viewport or represent it as a V. Okay, so this V indicate this is the viewport, and this W indicate in the diagram A as my window in the world coordinate system. Okay, now this is what is my original point. Okay, what is this? This is my original point I have captured in the world coordinate system, and this point is represented with the value xw comma yw. Okay, it is represented with the value xw and yw. Now along with this you can find which are the window edges. Okay, which are the window edges. Here I am having this point indicate the xw minimum, so minimum value of xw. Okay, so window x minimum value, and this indicate the window maximum value, xw maximum. Okay, so window x value which is maximum. Similarly we are having this value that we are represent as yw minimum, so the y value of the window which is the minimum value, and this I consider it is yw maximum. Okay, this particular point. Okay, now in some of the textbook or some of the books also refer this as, this is my left edge of window, this is my right edge of the window, this is my bottom edge of the window, and this is my top edge of the window. Okay, so within this context I am having the point which is captured by me, which is represented by xw comma yw. Okay, now I think we have written the same description of the diagram. Above diagram shows the window to viewport mapping. Okay, so we are just learning window to viewport mapping. A point at a position xw comma yw means this point at the position xw comma yw in the window is mapped into the position xv comma yv. So this is my, after mapping I will get this particular point xv comma yv. Okay, I will get this point as after mapping. Okay, which is associated in the viewport, because this is my viewport. Under the viewport I'm going to get it. Okay, now similarly as I am having the minimum and maximum value of x and y coordinate for the window, in viewport also we are having these values. So this indicate xv minimum. Okay, this indicate xv maximum. Okay, and this indicate yv minimum value, and this indicate yv maximum. Okay, now what it means is, these are, as I told, these are also called as viewport left edge, viewport right edge. We can consider this is my viewport bottom edge, this is my viewport top edge. Okay, or you can call it as yv. Y value we indicate viewport, this is maximum value, this is minimum value. xv, x indicate x coordinate value, we indicate viewport minimum value, and this is my maximum value. Now this mapping, okay, that we have to perform. Okay, I have to map this window to the viewport. Okay, I want to transfer this point which is captured in the window, captured by with the window or in the word coordinate system, and I want to map it to the point xvyv in my screen coordinate system or device coordinate system in a viewport with respect to viewport. This point is with respect to window, this point is with respect to viewport. Okay, so let us understand the which formulas or which equation I can use to transfer this xw comma yw into xv comma yv. See, this is my point xv comma yv. Okay, so I'm just moving to the next slide to understand the equation or the things in detail. Okay, I hope all of you cleared between the, or you have cleared with what we have to do. We have to map the window to the viewport. Okay, so I'm just moving to the next slide now. Okay, again I'm having the same diagram with me because we have to refer this diagram and we have to convert this point. Okay, our aim is to convert the point xw comma yw, which is represented into the window, to the point xv comma yv represented in the viewport. This is my v. Okay, now just let us understand how we can come to some equation to maintain the same relative placement. What I want to maintain, I want to keep the same relative placement in the viewport as it is in the window. So relative placement which is there in the window, I have to maintain it when I'm converting or mapping into the viewport. What we require that, so we require to know this equation. Okay, so let us understand what the equation we are having. Okay, so how I come to some equation is xv, my point is having, because I want to convert my xw to xv. Okay, so what is my, this is my xv, so xv minus xv minimum. Okay, xv minus xv minimum is divided by xv maximum minus xv minimum. So whatever the difference I am, so this is generally we call it as the displacement that we are having. Okay, max minus minimum, so I call it as maximum displacement of the xv. Okay, so xv minus xv minimum is divided by xv maximum minus xv minimum, which is equal to, now how it is represented into the window, so I'm having xw minus xw minimum. Okay, similarly, similar to this, okay, xw minus xw minimum divided by xw maximum minus xw minimum. So that is my displacement of x coordinate in the window, maximum minus minimum. Okay, now similarly this is for what, this is for the x value, okay, related to x coordinate. Similarly, I am having it for the related to y value. Okay, related to y coordinate, how I will achieve yv minus yv minimum. Okay, similar to this, yv minus yv minimum is divided by the displacement of y in the viewport or on the we can say screen coordinate system, which vy maximum minus vy minimum, which is equal to same. Now it is, this is the y displacement or y value in the window, so yw minus yw minimum divided by yw maximum minus yw minimum. Okay, so this is my displacement. Okay, now suppose, now the meaning of this is whatever the yw value I am having minus, okay, I having yw minimum value divided by the displacement. Now what is this displacement generally indicate is, so suppose I am having the window, I think we have seen in the, while we are learning the line drawing algorithm. Okay, so this is my suppose 100 value, this is my, suppose I take it as 400. Getting me? So my window is having x minimum value 100, x maximum value 400, my y value is again 100. Getting me? I am getting this y value is also 100, and what is why my maximum, suppose I take this as 300. Okay, so this is my 300. So you can find the difference between yw maximum minus minimum, so it is 200. So I'm dividing this value with the 200. What is my xw maximum minus xw minimum? So I'm having this 400 minus 300 means it is 300. So this difference is 300. This difference is 200. Okay, and respectively I'm doing. But now whether the same size I'm having for the viewport, here I'm having the xw minimum is 100, this is 400, this is 100, this is 300, but not necessarily I will have the viewport with the same value. My viewport may not be have the same value. For example, suppose I take my xv minimum is 100. Okay, I just take this value same as xw minimum, but now I'm having xv maximum is not 400. Suppose I'm having this as 300. Okay, so this is my value 300. This is suppose my yv I am having 100. Okay, no issue, but now I am having yv maximum is 200. Getting me? So see, this is the difference. Okay, now in this particular case, whatever the point I am having here represented as xw comma yw should be appropriately represented in the viewport. And what will be its value now? Okay, what is the value of xw yw? And when I go for this mapping, what should be my value in the viewport xv and yv, that we have to find out with the help of equation. And for that we have written this. Okay, now we are coming with the help of these equation. Okay, with the help of these values, I'm just moving to the next slide to understand the exact equation or to understand the correct equation. I hope all of you have cleared. This is the scope of the window, 100 to 400, 100 to 300. Within that, I have declared one point xw, yw. I have to map this point, okay, in the viewport, whose size is different than window. Window is having different size, viewport is having different size. What is the size of viewport? For example, this is 100, 300 and 100, 200. Okay, and now I have to find out the how this xw, yw, what is the value of xv and yv here. I may take suppose the value of this point. Okay, I'm just taking it as roughly. Okay, suppose I consider the value of xw is 150. Getting me? What is the value of this is 150 comma 150. Suppose I take it as an example. Okay, considering this as an example, I am having the value of xw yw is 150 150. Then what should be its value when it is mapped to the viewport? What its value should be in, that is xv and yv value? Definitely it is not 150 150, because the displacement here is 100 to 400, it is 100 to 300. In y, displacement in window is 100 to 300, but it's only 100 to 200. So obviously the point 150 150, that is xw yw value, definitely will not same as it is. It is going to change, and we have to find out what should be the value of xv and yv. Okay, so I'm just moving to the next slide now, just to understand the appropriate equation, okay, that we are having. I'm just moving to have appropriate equation now. I'm just continuing with the same diagram because this is what the problem we have to solve. Okay, now solving this equation, just now we have seen the equation. Solving this expression or equation for the viewport position xw yw, okay, we have, okay, what we are having. See, I can find out the value of xv and yv, which is equal to, so I think we have came some equation now. What is my xv is equal to? It is xv minimum. Okay, xv is equal to xv minimum plus xw minus xw minimum into sx. Okay, similarly I'm having yv is equal to yv minimum plus yw minus yw minimum into sy. Okay, where I'm having this sx and sy are my scaling factor, change of the scale. Why change of the scale is required? Because see, my window, scale of my window is different and scale of my viewport is different. Getting me? Scale of my window w is different, the scale of my viewport is different. Okay, It may happen this is more, this is less, or it may happen this is small and this is larger. It may happen depending upon how I have selected the window and which object I am representing in it. Okay, so this is my Sx and Sy factors that I'm having. Okay, what is my Sx now? My Sx is xv maximum minus xv minimum divided by, I think now we have came to the correct value, correct solution. Xv maximum minus minimum, so whatever the difference I'm having here, divided by xw maximum minus xw minimum. Okay, and that is my scaling factor. For example, in the previous example, okay, in the previous example, what I'm having xv maximum is 300, xv minimum is 100. Suppose I'm just considering it as example. What is the difference I'm getting? I'm getting the difference as 200. Okay, what is the difference I'm getting between the uh, x xv maximum minus xv minimum is 200, whereas xw maximum and xw minimum, so xw maximum is suppose 400, this is 300, so difference is 300. So I'm having the Sx is equal to 200 divided by 300. I think, I hope all of you understood it. So it is 2 by 3. Okay, so I'm just going to Sx value is 2 by 3. Now for Sy also I'm doing the same thing. For Sy, suppose I'm having Yv maximum minus Yv minimum. Okay, I'm assuming here Yv maximum is 200, this is 100. I think we have seen this in the last slide. Previous slide we have shown this. Okay, so suppose that difference is 200. Okay, no, not 200. I think it will be, suppose this is 100 and this is 200, so difference is only 100. Okay, so I'm having the value for this is 100. Getting me? Divided by what is my YW maximum and YW minimum. In the previous slide we have considered YW minimum is 100 and YW maximum is 300. Okay, so difference is 200. So here I am having the difference 100 divided by 200. Okay, that will be 1 by 2, means 0.5. What is my value of Sy? My Sy value will be 1 by 2 or 0.5, and my value of Sx will be 2 by 3. Okay, and this is my multiplicating factor, or this is my scaling factor. So this is what the equation, okay, that we are having. This equation will useful to convert the point or map the point xw comma yw represented in the window coordinate system to the point xv comma yv, to the point xv comma yv represented in the device coordinate system or screen coordinate system relative to the viewport. Okay, I hope all of you very much clear with the equation that we are having. Okay, so just now whatever the part that we have learned, okay, so this one xv and yv, how to calculate the mapping point xv comma mapping point yv. So I just continue with the discussion to show that it is possible to get it with the help of the sequential transformation also. Okay, now to just discuss this point or just to understand this particular point, okay, I'm just moving to the next slide. So again you can find here what was our conclusion. Our conclusion is, okay, mapping this point, how I can map this point to the this point. And I think now we have come to some conclusion here, some formula. That formula is xv is equal to xv minimum plus xw minus xw minimum into Sx, and yv is equal to yv minimum plus yw minus yw minimum into Sy. Okay, so this is what our equation or the formula for the mapping of the point xw comma yw to the viewport point xv comma yv. Okay, so this is what our transformation, this is what our mapping. We have considered this is my window, we have considered this is my viewport. Okay, now in this particular case, okay, now the same thing whatever we have came to this conclusion or came to this equation or the formula can be achieved with the normal transformation or the sequence of transformation. So just understand this particular point now. So see what I have written. Above formula can be derived with the set of transformation. Above formula can be derived with the set of transformation that converts the window area into the viewport area. Okay, because fortunately what we have to do, or actually we have to do, we have to convert the window area into the viewport area. So to achieve this, okay, I'm having the following sequence of operation. Okay, this conversion is performed with the following sequence of operation, or we can combine this sequence. I will get the composite transformation, and this is what my formula I get it. Okay, so what is my step number one? So my step number one is perform a scaling using a fixed point position. So what is my fixed point through which I am doing the scaling? My fixed point is xw minimum and yw minimum. So this is my, I consider this is my fixed point because I consider this is my origin of my scaling, which is the minimum value or 0 value of my window. Okay, this is my window and this is my 0 value. Getting me? So I'm going to perform the scaling using a fixed point position xw minimum and yw minimum. Okay, this was my step number one to achieve this. Okay, to achieve this formula. Okay, I can achieve this formula using this sequence. So I perform the scaling, that is a fixed point scaling, and then I will go for the step number two that scales. Now this xw comma yw minimums that scales the window area to the size of the viewport. So actually what I'm going to do is I'm performing the scaling so that the window area will be, I think just now we have written, we have to convert the window area into the viewport area. Okay, so this is going to scale the window area to the size of the viewport. Okay, and after that what we have to do, I think we have to, after scaling we have to perform the translation. Okay, translation of the point. Okay, so that's the second thing what I have to do is, okay, I think that is just now I told that we have to return translate the scaled window area to the position of the viewport. Okay, so the combination of the step number one, which is the fixed point scaling, and then the translation, again, that will achieve the mapping of a point xw yw, which is defined in the window, to the point xv comma yv, which was defined in the viewport. Okay, and this is something that we are considering or calling it as the windowing transformation. Okay, so I think, I hope all of you have understood this point in detail, how I can convert or how I can achieve this mapping. Okay, and this mapping is achieved with the formula. I repeat the formula again, xv comma yv. So how I get this xv comma yv? I get xv is equal to xv minimum plus xw minus xw minimum into sx. See, sx is my scaling factor. Okay, and what is yv? Yv is equal to yv minimum plus yw minus yw minimum into sy. So sy is my again scaling factor, and in the last slide we have seen what is the expected value of sx and sy, and how we have calculated the value of sx and how we have calculated the value of sy, that we have seen in the last slide, the formula for the same. Okay, so I consider this is all about the windowing transformation point, and we are learning this windowing transformation. Okay, now before we conclude the windowing transformation, I'm just moving to the next slide so that you will in detail understand what is mean by the window and what is mean by the viewport, or how exactly it is represented. Okay, how this window and viewport is represented. Okay, now to understand this in detail, I'm having the next diagram. Let us understand the next diagram, which will clear your concept, okay, of windowing transformation, and it also clear your concept of what is mean by window, what is viewport, and how it is represented. Okay, so I'm just moving to the next slide now. Yes. Okay, I want everyone to concentrate on this particular diagram, which will clears your all concept, okay, related to viewport, window, okay, then transformation of this. Okay, I first read what is the name of diagram and what we have written over here. It shows the mapping selected parts of a scene. Okay, what we are mapping? We are mapping some selected part of the scene in a normalized coordinates to different video monitors. Okay, because see, whatever we have captured in a scene, I may want to divide that part and I want to display some part on the different monitor screen with workstation transformation. With workstation transformation. Okay, so this may be my workstation 1, workstation 2, and so on. Okay, now just understand whatever we are learning. So I want you first to concentrate over here. I want everyone to concentrate on this particular diagram. See, this is my viewing coordinate window. Okay, so this is my viewing coordinate window. What is mean by viewing coordinate window means how I can visualize it, how I can visualize this in my windowing transformation. Okay, now when I am achieving this normalization, see, this is, I considered this is my window. Okay, this is my window. Obviously it is having workstation 1, this is my workstation 2. So whatever picture I have captured, okay, in my window, that I have converted, this is my picture which is captured. Okay, this is my picture or the scene that I have captured through my word coordinate system, which is normalized between the point 0 and 1. You can find it is normalized. So I'm having this as a normalized space. Okay, this is nothing but my window that I'm having. This is my window. Okay, see this rectangle, okay, whatever I have shown, I considered this is my window. Okay, so that I have captured. But this is how, where it is displayed on the screen. It is displayed on the screen with the help of the viewport, and my same viewport is again divided into two parts. Okay, one part or the left side part, I want to call it as the workstation 1, and the right side part I want to call it as my workstation window 2 or workstation 2. Okay, the one part means 50% of the scene I want to display on my monitor 1, and 50% I just want to send it to the monitor 2, means this part I want to display over here. So now this is nothing but this is my monitor screen. So means this indicates that I'm working on my screen coordinate system, or this is my device coordinate. This is also my monitor 2, means this is again my uh, screen coordinate system, or this is again my device coordinate system. Getting me? And now what I have to do, I have to map, I have to transform this particular workstation 1, and this is my viewport. If you're getting me, this is my viewport for my workstation 1. Means my workstation, I've divided it into two parts and named it as a workstation WS1 or WS2. Okay, workstation 1 and workstation 2. Okay, now this particular part I'm going to put it on my screen, monitor screen or screen coordinate system, and here it is displayed. It is in the form of the viewport. Now this viewport indicates that I want to display it at the center of my screen. Okay, I have decided my viewport to be in the center of the screen. Not necessarily it is at the center, it may be anywhere. Okay, similarly you can find that this particular part, which I call it as the workstation 2 window, and I want to display it on my monitor 2, second monitor, and this is my viewport. Okay, workstation viewport, and here again this is also at the center of the screen and I want to display. See, though this is not shown on this particular diagram, but for your better understanding I'm explaining this. See, your monitor screen is divided into multiple viewport. There is not necessarily only one viewport. Suppose I call this is my viewport number 1. Okay, then I may divide the screen that this will be my viewport number 2. I want everyone to concentrate here so that you will understand this is my viewport number 2. This may be my viewport number 3. Getting me? This is my viewport number 3. This is my viewport number 2. Okay. Now you can decide. So generally, that is what I want to mention is generally the viewport will not cover the complete screen. I repeat the sentence again. Viewport generally not cover the complete screen, but it is covered some part of your screen. Okay, cover some part of the screen. So suppose in the center I have displayed this, my viewport number 1. Okay, but I will use this viewport number 2 maybe to have different commands. Which are the commands? For example, I am happy with the whatever the object I am having, I may use the tab here or the button OK. Okay, or I may use the button cancel. I may use the button delete. I may use the button next and so on. Getting me? So I may have the different commands I can write in the viewport number 2. Suppose I am also using viewport number 3. In the viewport number 3, suppose I am having the command to edit. Okay, edit this picture or beautify this picture or crop this picture and so on. So I'm having different commands 1, 2, 3. I will use different commands in my viewport number 3. Viewport number 2, I may use the command OK, cancel, delete, next, previous. Okay, so what this particular thing indicate? See, this particular thing indicate that my screen is generally divided in more than one viewport. Okay, this is my viewport number 1 to display the object. See, I'm using my viewport number 1 to display the object. I use viewport number 2 to have different commands such as OK, cancel, next, previous and so on. I may have my viewport number 3. Look at this. This is my, I may use some part of the screen and call it as the viewport number 3 where I'm having the option edit. Okay, maybe the beautify this image, maybe the crop the image and so on. Okay, so what was my purpose is, whatever I have captured under this window using this window coordinate system, I want to map it to any of the viewport on my screen. Okay, and this is something that we are going to call it as a windowing transformation. This is the concept related to the windowing transformation. Okay, I hope all of you have understood with the help of this diagram. Okay, what is mean by the viewport? See, now this diagram is advanced diagram because this also shows that the viewport cannot be directly displayed on the screen, but it may be divided into different parts, and I can call it as workstation 1, workstation 2, and I can send the workstation 1 to the one screen or monitor screen. I display the workstation 2 on to the another monitor screen. So whatever I have captured in my word coordinate system, whatever the scene I have captured in my word coordinate system, I can divide it into the different workstation. The part of the scene can be considered as a different workstation, and I can map it separately to the different monitor screen. Okay, so this is what the mapping of the part of the scene. I think the diagram indicate mapping the selected part of the scene in a normalized coordinate to the different video monitors with the workstation transformation, along with the concept of the workstation transformation. Okay, so this is what is all about the concept that we are calling it as a windowing transformation. Okay, I hope all of you have enjoyed the concept learning of the windowing transformation. So we are going to end our session here. Okay, so thank you all the students, thank you all.